In this arrangement shown here, the frictional coefficient between these two blocks is mu, and the frictional coefficient between this capital M and the ground is 0. That means this is a frictionless surface, right? Now the question is, what maximum force F can be applied such that the equilibrium of this system is not disturbed? Okay, let's find out that. If I draw the free body diagram of small mass M here, you can see the force to be applied is towards left, and now this is the maximum force. That means on this right direction there will be the maximum friction, which will be mu mg, and also there is a tension over here, that is capital T, so I will write this as capital T. Now since this is still in equilibrium, I can equate these two forces, so F equal to mu mg plus capital T. And now let's look at the free body diagram of mass capital M. So if I look at this capital M, you can see the frictional force on the top block is towards right. So the frictional force of this block M on this block capital M will be towards left. Okay, so this will be in the opposite direction and the same magnitude, right? If this is experiencing a friction in the backward direction, then the same amount of force will be applied by small m on the big M in the left direction, right? So now there will be a tension towards right, and then there is no other force because there is no friction between capital M and the ground, so there is no friction between these two. So this will become T is equal to mu mg, right? Now you can substitute mu mg for T, T for mu mg. So if you do that, you will get F is equal to mu mg plus mu mg. So that will become 2 mu mg. So this is the minimum force that is required so that you do not shift the equilibrium of the system. Okay. Now let's look at the next part of this question, that suppose the horizontal force applied is double that of the value this which we have found out. That means horizontal force applied is 4 mg. If horizontal force is 4 mg, let's call it as F dash, then what will be the acceleration of the blocks? Okay, so let's look at the acceleration of these blocks. So now if you see here this diagram, in this diagram again the same thing we will do. On small mass M there is a force, now that force becomes F dash, so that F dash is double the previous value, that is 4 times mu mg. In the opposite direction there will be the tension because the string is pulling it towards back with a tension T. And what else will be there? There will be the frictional force, right? So it will be towards back, which will be mu mg, right? Now this block is moving, that means the limiting friction will be there, that is mu mg, because there is a relative motion. Okay, so for mu mg towards left, mu mg plus T towards right, so it will be accelerating towards left, so it will be 4 mu mg minus mu mg minus T is equal to ma. This is the acceleration of small block M. Now the acceleration of the big block capital M will also be the same because they are both attached to a same string, right? So if it goes with a certain acceleration towards left, capital M will go with the same acceleration towards right. So we will have for the capital M free body diagram like this. The tension is towards right. There is no friction between the ground and that block capital M because the ground is frictionless. So the frictional force between M and capital M will be towards left, as I told earlier. It will be mu mg, right? As stated earlier, it will be towards left. So now this block capital M will be accelerating towards right. So we have T minus mu mg is equal to capital M into A. This is the second equation. Now if I add these two equations, what I will get is 2 mu mg. Okay, 4 minus 2 mu mg is 2 mu mg. T and T will get cancelled. So this is M plus small m into A. So A value will become 2 mu mg upon m plus m. This is the acceleration, and note that the acceleration of the both blocks will be the same.